Can you believe it? In many countries, building a bridge is often just about solving a problem of crossing a river, spanning a road, or restoring traffic flow. But in China, bridge construction has long ceased to be just a matter of civil engineering. It is more like a massive coordinated campaign in which materials science, structural mechanics, fluid mechanics, wind engineering, geotechnical engineering, intelligent manufacturing, digital modeling, heavy equipment, precision surveying, and national-level project organization are all compressed into a single battlefield. And that is exactly why China has earned a name that hits with enormous force around the world. An infrastructure powerhouse. That label is not exaggeration. It is not emotion. It is not just an internet joke. What truly shocks the world is that China's bridge building technology embodies three things at once: massive scale, extreme difficulty, and astonishing speed. While many countries are still debating whether a bridge even needs to be built, Chinese engineers are already turning what looks impossible into reality. Across deep mountains, steep canyons, rushing rivers, complex seas, strong wind zones, earthquake belts, and the harshest geological environments. And what is even more frightening is not simply that China can build bridges, but that it can build them continuously in large numbers, with high efficiency, under conditions that are extraordinarily complex, dangerous, and demanding. What lies behind this is the real monster, the technological system. Because a bridge is never just a matter of stacking reinforced concrete into the sky. A bridge project is, at its core, a direct confrontation with nature. What you are crossing is never just water or a canyon. You are confronting wind, gravity, vibration, fatigue, temperature differences, corrosion, bearing capacity, construction error, material limits, and the demand for safety over decades, even more than a century. And the truly terrifying thing about China's bridge technology is that it is not merely strong at one point. From surveying, design, manufacturing, and construction to post-completion monitoring, it has formed an entire complete and highly formidable engineering chain. Let's start with the most basic step: surveying. Real top-tier bridge building ability does not begin when cranes arrive on site. It begins when you have the ability to fully understand the land beneath your feet, the water in front of you, and the canyon you are about to cross. Today, China's bridge engineering capabilities in early-stage surveying go far beyond the traditional meaning of simply measuring the terrain. Modern large-scale bridge construction often involves high-precision mapping, three-dimensional topographic modeling, geological radar, drilling and sampling, hydrological analysis, wind field simulation, seismic response evaluation, and even projections of flood variation, rock stability, and climate impact over decades. Because a bridge does not just have to stand up, it has to stay standing, keep bearing, and remain stable for decades to come. And what truly makes Chinese engineers remarkable is that they have become accustomed to starting work in the hardest places. The higher the mountains, the deeper the valleys, the faster the water, the softer the soil, the more faults, karst caves, landslides, and corrosive environments there are, the more these conditions force out tougher and more mature technical solutions. In other words, China's bridge technology was not trained in a standard test room. It was forged level by level inside hell mode environments. Then comes design capability. Whether a bridge can be built is not just a matter of courage. It depends on whether you can calculate every extreme load condition clearly. Chinese bridge design is no longer living in the age of simple two-dimensional drawings. Today, many major bridges have already entered an era of digitalization, simulation, and fine-grained precision at the design stage. How the wind blows, whether the bridge will sway, how traffic loads move, how forces change, how temperature differences are transferred, whether the structure will deform, and how towers, main girders, cable systems, and foundations interact during an earthquake. None of this is left to rough judgment or instinct. It is tested through huge mathematical models and countless rounds of simulation. What does that mean? It means that in Chinese bridge construction, engineers are no longer saying, "Let's build it first and adjust later." Instead, they are saying, before construction even begins, we have already rehearsed the most dangerous scenarios countless times inside the computer. That is what makes China's bridge technology so frightening. It is not brute force. It is ruthless precision, followed by powerful execution. Then there are the materials and structural systems. When people watch bridge construction sites, they are usually drawn to soaring bridge towers, giant steel girders, and breathtaking lifting scenes. But what truly determines the upper limit of a bridge is its material system and structural system. One reason China's bridge technology is so strong is that it has already developed a very mature understanding and application of bridge materials. From high-performance concrete to high-strength bridge steel, from fatigue-resistant welding technologies to wind and earthquake-resistant structural design, from anti-corrosion systems to lifespan management, China is no longer just using these things. It is optimizing combinations for different scenarios. And that matters, because a bridge is never safer simply because it is heavier, and it is never more advanced simply because it is thicker. Truly advanced bridge engineering is about finding balance between strength, toughness, weight, durability, construction convenience, and long-term maintenance cost. It must carry tens of thousands or even hundreds of thousands of tons in load, while also enduring strong winds, rainstorms, heat, freezing cold, salt spray, and the erosion of time. It must be controllable during construction, safe in operation, and reliable decades later. And in this regard, China has already pushed bridge engineering from merely being able to build to being able to build optimally. Then there is construction equipment. This is perhaps the part that most easily shocks ordinary viewers, because you quickly realize that when China builds bridges, it often looks less like traditional construction and more like a steel spectacle starring heavy industry and intelligent equipment. Giant launching gantries, 1,000-ton lifting devices, cable cranes, intelligent pushing systems, girder transport vehicles, ultra-high pumping systems, automated welding systems, large-diameter drilling machines, deep-water foundation platforms. The existence of these monster-level machines directly turns what used to be too difficult to build, too difficult to install, or too difficult to cross into a question of how to solve it faster, more precisely, and more safely. To put it bluntly, what makes Chinese bridge construction so powerful is not just that the workers are willing to fight hard. It is that the equipment system has grown strong enough to turn the limits of human physical strength into the precision limits of mechanical systems. In the past, bridge construction relied heavily on manpower, experience, and on-site reaction. Now, China's large-scale bridge building is increasingly moving toward industrialization, modularization, mechanization, and intelligence. Large numbers of components are prefabricated in factories and then transported to the site for precise assembly. Many key nodes are no longer controlled by close enough thinking, but by millimeter-level precision. Many high-risk, high-difficulty, high-altitude, and hazardous operations are gradually being taken over by mechanical systems, automatic monitoring, and digital control systems. That means bridge construction is transforming from a heavy manual project into a high-precision industrial process. And that is one of the strongest reasons why China's bridge technology feels so far ahead. Now let's talk about construction methods. What truly earns respect for China's bridge technology is not just that it has powerful equipment, but that it knows how to push a wide range of construction methods to the limit depending on terrain, span, and environment. How do you build deep water foundations? How do you erect super high bridge towers? How do you transport the main girder? How do you close an arch rib? How do you tension stay cables? How do you control the shape of a suspension system? How do you assemble high-altitude segments? How do you lift massive components in strong wind conditions? Every one of these questions, by itself, is a world-class engineering problem. And through long-term practice, China's bridge engineering industry has built an extremely powerful toolbox of methods. Rotation, incremental launching, cantilever assembly, segmental erection, integral lifting, synchronized sliding, intelligent tensioning, precision closure, high-altitude cable lifting, deep water cofferdams, giant caissons, large diameter pile foundations. These terms may sound technical, but behind all of them is the same reality. China has developed the ability to find a way, put up a bridge, and compress errors to extremely low levels under all kinds of extreme conditions. You can think of it this way. China does not have just one method for building bridges. It has an entire arsenal. Facing different terrains, it can change tactics. Facing different spans, it can change structures. Facing different risks, it can change methods. Facing different construction schedules, it can change organization. That is what real engineering strength looks like. And do not forget, bridge construction has never been simply about building. It is also a control game against time. You have to control schedule, cost, error, safety risks, and the changing stress distribution of the structure as it takes shape. Many major bridges, before final closure, are actually incomplete structures whose internal forces are constantly shifting and being redistributed. At that stage, even a small deviation can trigger huge cumulative errors. And what really commands respect about Chinese engineers is that they have already brought this kind of process control to an extremely high level. From surveying control, cable force control, and alignment control, to temperature compensation, wind deviation correction, construction simulation, and real-time monitoring, Chinese bridge construction is no longer just putting things into place. It is a constant process of calculating, correcting, and pushing closer to the theoretical optimum. That is why behind those shocking construction scenes, what really exists is a kind of almost cold precision. It is not hot blood or brute courage that gets a bridge built. It is that behind every lift, every assembly, every push, every weld, and every tensioning operation stands a complete and rigorous technical control system. If we go one level deeper, the real power of China's bridge technology lies in the fact that it has already completed a leap from strong in individual technologies to strong in overall systems. Many countries may have experience with one certain bridge type. They may have their own strength in a particular design concept. They may have long-term accumulation in one class of materials. But what truly shocks the world about China is that it has nearly connected the entire chain. Design institutes, research institutions, equipment manufacturing, construction enterprises, material supply, digital platforms, on-site management, and long-term maintenance. In other words, it is not just that one genius engineer is impressive, or that one construction company suddenly breaks out. The entire civil engineering system is running efficiently. And when a country has that kind of systemic capability, what happens? What happens is that bridge building stops being just a single project. It becomes a national industrial capability that can be continuously replicated, continuously iterated, and continuously upgraded. Today, you solve one type of deep valley bridge challenge, and tomorrow, that experience can be transferred to another kind of mountain bridge. Today, you break through in one cable erection technology, and tomorrow you can replicate that in larger spans and more complex wind conditions. Today, you push high-altitude closure error down to extremely low levels, and tomorrow you can standardize, equip, and industrialize the entire process. That is what makes China's bridge technology truly terrifying. It evolves. And it does not evolve slowly. It evolves rapidly through huge numbers of projects, complex environments, and constant real-world application. There is also another point that cannot be ignored. China's understanding of safety and service life in bridge engineering is also continuously upgrading. Truly top-tier bridge technology is not just about building spectacular bridges. It is about making sure the structure remains monitorable, maintainable, and predictable over decades of service. Today, many bridges begin operating with complete health monitoring systems from the moment they are completed. Cable force changes, vibration response, temperature fluctuations, displacement, stress states, and fatigue accumulation can all be sensed in real time. That means China's bridge technology is no longer just about building bridges. It is moving towards smart bridges and long-term service management. Completion is not the end of a bridge. It is the beginning of another technical system. So when people call China an infrastructure powerhouse, what truly earns respect is not just the towering pylons, not just the thrilling scenes of high-altitude lifting, and not just the spectacular image of a bridge crossing rivers and canyons. What truly leaves people stunned is the fact that behind those scenes stands an engineering capability that is incredibly mature, incredibly vast, and incredibly efficient. It can find solutions in the most complex environments. It can maintain precision under the most dangerous load conditions. It can replicate experience across construction on a massive scale. It can push bridge building from traditional civil works into a new stage of digitalization, industrialization, and intelligence. That is no longer simply being able to build bridges. That is turning bridge engineering itself into a display of national technological power. While many parts of the world still see a bridge as transportation infrastructure, Chinese engineers have long since turned the bridge into a hardcore technological expression, a way to break through geographic barriers, reshape spatial patterns, compress time and distance, and challenge the limits of engineering. To put it even more directly, what makes China's bridge building truly extraordinary is not that it has built one bridge, but that it has mastered the ability to build bridges stably, precisely, and efficiently under conditions that are almost impossible. Behind that is technology, its equipment, its materials, its design, its organization, its construction, its monitoring, and above all, it is a national capacity to keep pushing complex engineering to the extreme. So when you see steel girders advancing through the sky, bridge towers piercing the clouds, giant machines moving slowly through canyons, and tens of thousands of tons of components being lifted with absolute precision, what you are looking at is not just a construction site. What you are looking at is China's bridge building technology, rewriting the words impossible into reality again and again.